Okay, good afternoon, everyone. Welcome. Welcome to the University of Pretoria. My name is Yashay Narayansamy, and I'm a lecturer in the Department of Civil Engineering. Tonight, I'm speaking in my capacity as the Gauteng representative of GeoDev. Okay. Before I start with the lecture, I'd just like to talk about some housekeeping. The bathrooms are out the door. We turn right and then left, and then in the center of the building. For the online attendees, please write your name and surname in the chat. That's for CBD purposes. For everyone in person, there will be some registers. We'll circulate those if you can please just sign that. And then finally, after the lecture, just in the hall outside, we'll have some snacks. So please can you join us for that? Okay, thank you for taking the time to be here. We really appreciate your company. And this evening, we are honored to have Professor Lidija Zdravkovic from Imperial College London. Professor Zdravkovic is in South Africa as part of a recently initiated research collaboration between the University of Pretoria and Imperial College London. In March, Professor Jacobs and I traveled to the UK to visit Imperial College, and now Professor Zdravkovic, Professor Potts, and Dr. Gaspar from Imperial College are here to visit UP. Please allow me to share a little bit about Professor Zdravkovic with you. She was born in the Republic of Serbia, which is a country located in Central Europe, and she obtained her BSc and MSc degrees from the University of Belgrade. In 1992, she enrolled for a PhD at Imperial College London, and after successfully completing her PhD, Professor Zdravkovic soon became a member of academic staff, and she's been actively involved in teaching and research at Imperial College ever since. Professor Zdravkovic is currently a professor of computational mechanics, and amongst her many well-deserved achievements, I would like to share three with you tonight. Professor Zdravkovic served as the head of the Geotechnical section at Imperial College from 2014 to 2024. She presented the prestigious Rankin Lecture in 2024, and she is currently the editor-in-chief of the journal Geotechnical. I think we can all agree that we are truly fortunate to have such a remarkable person here this evening to speak to us. Tonight's lecture is titled Application of the Unsaturated Modeling Framework in the Assessment of Geotechnical Infrastructure. Please join me in welcoming Professor Lidija Zdravkovic to the stage.
Good afternoon, everybody. Yashay, thank you very much for your kind introduction. I did do my PhD in the lab at Imperial between 92 and 96, so I do still own lab coats, and I still have some research in the laboratory. So the objective of the lecture today is to talk a bit about my current research is mainly in numerical modeling. And the objective is to talk about the unsaturated soil behavior and how we take that into our computational analysis of real geotechnical problems. Before I do that, I ought to recognize that this is not just my research and give you a bit of a context of how we do numerics at Imperial. Most people will associate, firstly, soil mechanics in the past, now geotechnical engineering group at Imperial, with the experimental testing laboratory. From the time of Professor Bishop, Professor Skempton, many of the apparatus currently in use around the world has been designed by Professor Bishop and subsequently by some of our technical staff that some of you know very well. The other part of our research, also from those early days, is field testing and monitoring. So going in the field and here having a rig of instrumented pile being pushed into different soils to enhance the design methods for driven piles. And then instrumentation, developing some of the sensors, but also going into the live national infrastructure. My colleague Jamie Standing last year was here to give a lecture about this, and placing fiber optic sensors or many other sensors in tunnels or on the ground surface to monitor deformations. And then the third part of our research is computational analysis, computational geomechanics, that started to develop with Professor David Potts in the early 80s when he became member of staff at Imperial. And we developed our own code from scratch. So it is very simply called ICFEP, Imperial College Finite Element Program. It is fully coupled with thermo, hydromechanical, chemical and other processes in the soil. And we developed the actual nitty-gritties of numerical algorithms, but also constitutive models, boundary conditions, and then apply in the range as we developed over it. This is not all developed at once. We still develop the code as the problems in geotechnical engineering keep coming out, being requiring new answers to be devised and explained. So the research approach that we've always had, in particular in numerical modeling, has been this continuous interaction between the laboratory and the field, getting the input to numerical modeling from the laboratory, analyzing, predicting the behavior of geotechnical structures, and then, when possible, having the precious monitoring data to validate our predictions, and then go back and instruct the laboratory what other tests need to be done to define the parameters of the soil behavior that we need in particular applications. In addition to this, we have always worked very closely with industry. From the early days, David Potts has always been engaged with offshore developers, in early days oil and gas, then infrastructure with earth dams, embankments, slopes, working with London Underground because of the metro network, with Network Rail, with Environment Agency for flood defenses and things like that. And then more recently, so obviously tunneling, deep excavations, that is the bread and butter type of work. More recently moving to, as the demand for energy transition grew with so climate change and reduction of carbon emissions, working on foundation systems for offshore wind farms, as well as with thermo-mechanical coupling with thermoactive geostructures to use the potential of geothermal energy to translate that into effective heating and cooling of buildings, and nuclear energy, and so on. So this is the framework within we have operated for over 40 years. As I said, we are still developing the code and still carrying on with our numerical work. And what I would like to do in the next 45-50 minutes is talk about the unsaturated, specifically unsaturated modeling framework, because this is talking with colleagues here at University of Pretoria. This was identified as of a particular interest for problems in engineering problems in South Africa. So the three fields that I will talk about is the earth field infrastructure, how we use this framework for dams, embankments, natural and cut slopes based on the UK engineering practice. The radioactive waste disposal solutions may not be an obvious thing, but this is very important for the UK because the solution is using highly swelling clays as engineered barrier for this disposal. And then tailings facilities is something that we have started to work with more recently, again, engaging through students' projects, master projects, final year projects with different companies to address certain problems that they would like to see, what they mean, what the mechanisms may look like in certain situations. So starting with earth infrastructure, The objective really for using numerical analysis often is, and in the UK that is currently very frequent demand, this word of life cycle assessment of infrastructure from being constructed to at least 120 years in the future is a design life for most of the, let's say, structures that are currently being built or have been built on our most recent project is high-speed rail. So all the cuttings, cut slopes, tunnels, they are required to be designed for 120 years design life. So when we look at this sort of short and long-term assessment, this life cycle has always been in geotechnical engineering, because that is what we do. We often have short-term solutions, short-term stability, long-term stability, serviceability. And in this case, I will concentrate on this, what I call here exposed infrastructure, because we have here not just the soil-structure interaction, we have the interaction with the atmosphere, so precipitation, temperature, as well as interaction with the vegetation. So most of the slopes in the cuttings or in embankments are vegetated, and that causes issues in sort of maintenance. So the question here is, what is that we need to quantify in this life cycle assessment, and how? And here, through these three sort of settings, I would really go through the development of the approach over the years as the demands for assessment grew in engineering practice. So starting with sort of delayed failure of infrastructure slopes, if we look traditionally in classical ULS assessments of cut slopes, factor of safety has always been a parameter to quantify the short and long-term stability. So talking about, again, UK, we are dealing with London clay, usually as our material, so low permeability, high plasticity clay. If we are excavating a slope in a ground that initially has some groundwater level, at the end of that excavation, the phreatic surface will be depressed, and we would have a factor of safety in short term that will be affected by some suctions there that are developed above the phreatic surface. And if we then have the time transition from short to long terms, the equilibration of pore pressures, some final phreatic surface will be at a steady state somewhere here, and then the long-term factor of safety is likely to be lower than the short term because of these suctions now depleting with time. And what we traditionally do is perform an undrained analysis to calculate a short-term factor of safety, and then drained analysis to calculate the long-term factor of safety. But in reality, the soil behavior really is transitional between the two. And in terms of computational analysis, finite element analysis, so these are typical, this is typical equation, governing equations for saturated soils. So this is where we started back in the 80s and 90s. We have just displacement, degrees of freedom. And in terms of soil properties, we are worrying about shear strength and stiffness. And then hydraulic properties, we need to use a bulk modulus of the pore fluid, which is a high value for undrained analysis or 0 for drained analysis. So reasonably, from today's perspective, reasonably simple finite element setting. The problem started to appear in the 90s when some of the slopes, these cut slopes that were constructed decades before, started suddenly to fail. Although their original design had a sufficient factor of safety, these slopes started to fail some years after excavation. And the reason for this was attributed to a progressive failure but there was without numerical analysis, it was difficult to actually quantify and demonstrate that mechanism. And so for this reason, then, we have to move to transient analysis, to coupled analysis, because this is neither drained nor undrained state. It is a state somewhere in between those two limits. So hydromechanically coupled formulation for saturated soils requires a pore pressure, degree of freedom, and then some coupling matrices and permeability of the soil, as well as compressibility of the pore fluid, in addition to what we do with the mechanical aspect of the soil. And therefore, we need to now look at the soil behavior more closely, because this type of failure will appear in the soils like London clay, so stiff, over-consolidated clay, plastic clay, that in our traditional QP diagram will have a peak and then reduction of strength to some residual value post-peak over a certain deformation here. So in these early days, we have used a reasonably simple constitutive model, more Coulomb model, but allowing that model to have strain softening from peak to residual, both in terms of phi dashed and in terms of cohesion. And the rate of softening for London clay is from 5%, where the peak strength appears, to 20% at residual value. We have to also worry about then permeability of London clay, and in particular the field permeability of London clay, because intact permeability obviously is not that representative in the field. London clay, again, being over-consolidated, is also a fissured material. And so the scatter that we see, so permeability versus depth, is reasonably large, which is, again, people working in the field would recognize how notorious it is to actually measure the permeability of any material. But this is what is obvious here is that the permeability reduces seemingly with depth, but actually not depth. It is permeability that reduces with stress level, and we, in our treatment of London clay, we use an exponential function, so K naught is permeability near the surface, and then it is dependent with mean effective stress, so it reduces as the mean effective stress increases with depth. So the other thing that now comes important to introduce in the analysis, when we simulate this excavation and we end up having this new boundary, so starting from the reasonably horizontal ground surface, we have a slope and then the base of excavation, is hydraulic boundary condition. So in terms of, at the time, pore water pressure, that is our degree of freedom, our colleague, Professor Peter Vaughan, was very much, for his 40 years at Imperial, he was very much working with earth dams, embankments and cut slopes, and collecting measurements, again, pressures, field measurements of variations, seasonal variations of pore pressure, here expressed in head rather than pressure value. But we see measurements from natural slopes, cut slopes, embankments, minimum in the summer, maximum in the winter. But we see these suctions near the surface of the slopes, maybe 40, 50 kPa, and then in winter going to hydrostatic. So it is not unreasonable to assume some sort of average, maybe we can vary it seasonally, but maybe throughout the year, the average value of suction at the surface of a slope maybe between 0 and 20 kPa. So taking these now elements into our finite element analysis, but coupled finite element analysis to simulate this same process with this particular geometry of a cut slope here, we could see, so Dave and his researchers at the time together with Professor Vaughan, could demonstrate that slow progression of residual surface. So it starts from the toe, part of the surface is then, of the strength in the future failure surface is between the peak and residual, and part is somewhere at peak or before peak. So the shear zone clearly develops, and in this particular case, for this geometry, failure happens 14.5 years post-excavation, and vectors of ground movement show very clearly that failure. And with this, at that time, Dave and again his researchers were able to then explain to industry, to London Underground, to Network Rail, what are the conditions, what other ground conditions would affect this projection of how long the slope would be stable. Plotting here the horizontal movement in the mid height of the slope versus, horizontal movement this axis, and time on the horizontal axis, how the K naught in the ground affects the length of stability. But you can see these cuts, vertical sort of cusps, indicate that these are very sudden failures when they happen. How the slope inclination affects it, and also how this pore pressure boundary condition affects that stability. And most importantly, how the softening rate affects that stability. So for London clay softening rate, which is something that we call here low softening rate, for a slope of these dimensions, the shear surface may start to develop, but then it remains stable for all 120 years of the expected design life. But for our stiffer, older clays, like Kimmeridge clay, like Oxford clay, that have much more rapid softening rate, the same slope would fail after 21 years. So with this modeling framework, we started to be able to essentially quantify both the soil parameters as well as ground conditions that would affect the stability and serviceability as well, and also quantify the life expectancy of such infrastructure, not only slopes but embankments as well. But this was all done at the time, but we had a moderate climate. Peter Vaughan was measuring very repetitive changes in the seasonal changes in the pore pressure, and we could use pore pressure boundary condition. But when we go further afield, where we have situations in areas where the rainfall is the main driving force to inducing landslides or mudslides, and then more recently in the UK as well, after heavy rainfall, we very frequently see a slip like this in an embankment, or a slope getting deformed because the climate has started to change. We have more and more heavy rainfall from the post-tropical storms from the West Atlantic, and their intensity, really from the records that go from 2000 onwards, the intensity is much, much higher. So with the framework that we have, which is also a saturated framework, we can't really tackle problems like this. And that is where the evolution then of the modeling framework comes, having to take care of the interaction between the soil and the atmosphere in terms of rainfall, but also at the same time take care of what the vegetation is doing in the slopes and embankments, so the whole soil, atmosphere, vegetation interaction, because the roots of the vegetation will be taking the water out at depth, and that depends on the suction in the soil. Evaporation is happening from the ground surface, and then so rainfall comes in, and then it either goes into the ground or runs off. So we have to move then from this boundary condition to actually taking account of rainfall itself directly. And so we need to develop boundary conditions now, like precipitation, which is a dual boundary condition that will either allow infiltration into the soil if the permeability of the soil allows it, or if it doesn't, then it will essentially run off. We need evapotranspiration boundary condition to deal with the vegetation. As I said earlier, the potential evapotranspiration depends on the root depth, the suctions that are developing at that depth. But how much actually will transpire depends on the suction in the soil. And that is the modification of that potential evapotranspiration in terms of suction in the soil, because roots will not function if the soil is fully saturated, if the soil is waterlogged. They will also not function if the soil is completely dry. So changes in suction with a very simple distribution presented here, which comes from measurements in agriculture, is the modification that gives us that possibility of water to be taken out through evapotranspiration. We also need to change our constitutive mechanical model for the soil, and here we have adopted the Barcelona basic modeling framework, one of the first and one that has lasted the longest and been proven, but also enhanced with various other developments. This modeling framework allows us to take account of the strength increase in the soil due to suction, because that is what suction would do. So in our deviatoric stress, mean stress diagram, that allows us to go onto negative side of the stresses. In the suction mean stress plane, that is again the increase of strength with suction from saturated to further unsaturated conditions. And most importantly, this model allows us to model this constitutive model allows us to capture the load-induced collapse in the soil, because rainfall infiltration will flood or can flood the soil, destroy the menisci of the tensile forces that are holding the particles together, and therefore cause the collapse of the material. The saturated framework cannot give us that. If we put more water into saturated soil, it will just heave. So we need this framework to actually model what is more realistic. And then in terms of the volumetric behavior, hydraulic behavior, we have something like a soil water retention model that is usually expressed in terms of how the degree of saturation varies with increasing suction. Simpler models are simply non-hysteretic, whereas more advanced models would have hysteresis for drying and wetting of the soil, and then also be able to capture more realistic soil states that are in between these limiting curves. And most importantly, it is the permeability that we have to worry about here, hydraulic conductivity, which again, what we found out again when we started to develop, needs to have a dual function, needs to be a dual model that will capture the reduction of saturated permeability with increasing suction, because increasing suction causes the soil to shrink, to reduce the void space, so the permeability will reduce, and that is this looks all linear, but it's actually a logarithmic function of suction. And if we have only that model, then at some point, because the permeability is in units meters per second, permeability will become so small that the rainfall infiltration, which is also in meters per second, would not be able to get into the soil, which may not be realistic. When we look at the soil that shrinks and cracks, it has actually the desiccation cracking here, the cracks that increase the bulk permeability of the natural material. So what we have here is the permeability increasing depending on the tensile stress in the soil. And that, again, is a logarithmic function that will allow the water to go in if it eventually wants to, and if there is a cracking, desiccation cracking in the soil. So the governing equations become a bit more complex, in particular if we want to introduce a temperature as well as a degree of freedom. So 3 by 3 matrix. So here in hydraulic properties we have degree of saturation, the gradient of the water retention curve that goes into this part here, and then thermal properties, conductivity, volumetric heat capacity, and so on that need to be known about any soil. But what we can now do with this framework? So this is now unsaturated framework, and going to a slope in London clay, we have, this is a record of from a particular weather station in London, where we have 30-year record that we have interpreted here in meters per month, infiltration and evapotranspiration. So precipitation rates are here in pink. Evapotranspiration rates are in green, and they indicate this that much more water being taken out in the summer months. In the UK, from May to September is the summer period, and then in the winter we have much smaller evapotranspiration during the wet period. So the net water balance in the summer is taking water out, and in the winter water goes in. So we can start now to actually apply this life cycle analysis in great detail by starting with, this is a particular site where there was there was forest before, so trees there, with a high 2-meter root depth, so high water demand for the roots. And for about 9 years, we cycle this typical year until we get stable initial pore pressures at the end of the August period, so end of the summer, and the end of March period, which is end of winter. We can then simulate the excavation of the slope, and in year 10, let's say, and for the next 10 years, control the growth of vegetation to some low shrubs, low water demand to root depth of 5 meters. Precipitation is there all the time. And we can see, this is from numerical analysis factor of safety. This is not taking it out. This is an algorithm that we developed and dependent on a constitutive model and implemented in the code. We established some factor of safety in this slope of about 1.4, but you can see that there is, which is what we would expect, there is a slight difference between the factor of safety value in March, which is end of winter, slightly smaller, and slightly larger in the summer, end of August. And then, as it happens, maybe another 10 years, nobody controls the vegetation, and the trees grow again. So again, high water demand, and the factor of safety in the slope grows over those 10 years, again with a slight difference between August and March stability to something like 2.2. And then somebody sees that vegetation has now obstructing the signs, and the decision is made just to cut the vegetation down to nothing, to grass. And for the next 10 years, if this stays maintained at grass level, then we have here we see a rapid, so not rapid, but gradual reduction in the factor of safety to practically bare stability of 1.5. So within 5 years, because there are no trees there is no suctions in the soil, the precipitation, which cycles all the time, will gradually reduce that stability. And we can see that in the vectors of ground movement for the same 3 cases here. So at the beginning, quite a lot of mechanism here is quite deep, because quite a lot of soil needs to be mobilized for this to fail, whereas somewhere here, this is already very shallow failure that is nearly there to go. So with this numerical approach now, we are able to take rainfall into the analysis and to look at these antecedent conditions before, just before the rain comes, what happens. And what is missing now, we are able to do a full life cycle analysis, but we are not able to look at the future effects of the climate change. Because that is the part in the UK in particular, we have now legislation that, because of the legal obligation to get to net zero by year 2050, this document here, PASS 2080, this is the document that projects to year 2080, came out in 2023. It sets out for industry various clauses. I'm just here having one clause as an example to say prioritize nature-based solutions to reduce whole life carbon emission and so on and so forth. So this bit now, to predict what is going to happen, we need to do something else, because previously we were just using the existing known rainfall records. So the effect of future climate change now requires us to work a little bit with our hydrologist colleagues and see how they model these projections. We're working with our colleagues in the environmental section at Imperial. And so here I'm repeating this rainfall record for a particular weather station in Essex, which I will use for the next example. But the approach that these colleagues at Imperial have is actually to develop this from scratch. Today, there are predictive tools that are available online for getting to predict how the rain will look like in the future on any particular in any particular place. What our colleagues do is, first of all, take the existing record, which shows here, incidentally shows the big storms in 2013, 2014. 95 millimeters is the highest daily rainfall. And they, first of all, produce a synthetic record that is has the same sort of volume of rain coming as the real record, and has the same statistical characteristics like mean, covariance, skewness, and so on as the real record, because they want to take that synthetic record then in combination with the climate parameter projections to do lot more statistical analysis to get the projection of rainfall to year 2080. And these climate parameter projections in the UK are already there, so that is a database developed in 2018 that gives the projections of parameters like temperature, pressure, dew point, and so on to year 2080. And without going into details of how all of that works with these sort of two types of models, this is what we get for this weather station in Essex. So this is yearly rainfall, just for visibility, presented like this from the period time when we took the data, 2020 to 2080. This graph is a summary of 100 statistical analyses with the variations that are available here, and with a base synthetic model that has come from the real rainfall record. The gray zone represents 80% range of predicted rainfall, and the red line that you may see here is one simulation that we are going to take into our deterministic geotechnical analysis. So the example here is an example that we took to analyze because it had some field measurements to help us validate the model. So what we see here is a typical railway embankment on London clay foundations. These embankments are very old, probably 100, 150 years, constructed from just clay fill, clay lumps dumped on site, and therefore over time to maintain the level of rail, other material was added as this was deforming. Other material was added on top to actually keep that level. Initially, locomotive ash while steam engines were running, and more recently ballast that comes from either from commercially or from reuse of some other material. And what happened here is that, again, because of the obstruction of a network rail line here, these trees were removed, and the embankment was monitored for 5 years, for the whole year 2006 to 2007, to establish what are the stresses and movements in the embankment. Then trees were cut in March 2007, and then monitoring continued for another 4 years to 2011. So this is, again, here we do our life cycle analysis. Here this was an agricultural land, London clay, weathered and unweathered London clay. We treat now weathered London clay as unsaturated, as we did before. And we have grass again. We apply some average rainfall for a certain period of time. We then construct the embankment there. We then have 25 years, further 25 years of average rainfall, and we allow the growth of these mature trees on the slope of the embankment. And then 2006 to 2020, we have the removal of the trees in 2007 and these measurements. And from 2020 then, we apply our projection of 60 years rainfall to 2080. And so using the measurements to validate the model first, looking very briefly here at the mid-slope cross-section. The graph here shows the vertical displacements, negative values of settlements, and this is the year March 2006 to March 2007. So again, this is a typical seasonal variation in vertical deformation of shrinkage during the summer period, which is causing settlements here, and then from September onwards, the rainfall, the wetting is causing the swelling back of the embankment. In that September, at the end of the summer, we have quite high suctions because of these trees, 50 kPa in the embankment, 100 kPa down in the foundation soil. And then in March 2007, before the trees were removed, these suctions have gone down because of the infiltration, rainfall infiltration. And then the trees are cut, so that boundary condition stops of the roots. And by September 2007, there is hardly any change in this in these suctions here in the embankment compared to the previous September, because there are no trees there. There is no water being taken out. And we look again here at vertical displacements in these cross sections for the next 4 years. Essentially, the embankment is heaving. And the numerical model, both in the previous case here and in these 4 years of available measurements, is capable of capturing these movements at these two points. But what we now want to look at here, what is of interest with this life cycle analysis? This is now the projection. What I'm plotting here is elevation, again in this cross-section, versus horizontal displacements. And on this graph here, the pore pressures. So we have, for each of the decades that we go to from 2006, 2009, and then 2070 to 2080, the 10 lines here. Sorry, the resolution here is not very clear. But what we see as a consequence of the tree removal, of the removal of those trees, we have quite a lot of ratcheting. I know because of the colors that are supposed to be here. This ratcheting is happening even in the current decade, 2020 to 2029. And then it slows down. The conditions on the slope remain the same. That was one of the analyses conducted. But they start to indicate perhaps a slippage between the London clay fill and the foundation soil, maybe up here as well between the London clay fill and ash. But that is what life cycle analysis can provide. Is there any danger for any future instabilities? Of course, the rainfall is there. The rainfall is applied constantly. In this case, that doesn't seem to be much of a problem. But if it was, then certain measures could be devised to prevent that. And we can see the drying out, because that projection of rainfall until year 2080 was indicating that the area will be sort of drying out because the rainfall was reducing, and here the suctions are definitely increasing to year 2080. This is in the summer. Obviously, there is a recovery in the winter. And we can also then have a spot checks of stability to storm and antecedent conditions. So we have 95 millimeters per day was the highest rainfall. Applying that rainfall in the embankment that was in the wettest summer, when the factor of safety before the storm was 1.6. After the storm really doesn't change because the embankment is reasonably saturated and most of the rain has just run off. But in the dry summer, which was projected to be in year 2069, the factor of safety here, 2.12, is quite reduced, so the embankment remains stable, but there is quite a dramatic reduction in that factor of safety due to rainfall. So this is what we become able to assess with this modeling approach, because we have essentially all the ingredients that we can control to a certain extent. So we can bar the statistical analysis that involves the projection of the rainfall, where obviously there are many combinations and many aspects of what one takes, which parameter one takes into those projections. We can have a reasonable projections in the future. So this modeling framework as it is, we are now going to apply to a different boundary condition, radioactive waste disposal, and it will become a little bit more complicated. There's not going to be rainfall here as such, but we're talking now of highly swelling clays, And in the UK, because UK does have nuclear energy within the energy mix, we have lots of waste from the existing power stations, and government has a couple of years ago made a decision to actually invest more into nuclear to for this green, clean energy. Wind is already very much developed in the UK, and nuclear is aiming to have a similar proportion in the energy mix. So the radioactive waste inventory in 2022 showed that there is already 4.5 million cubic meters of waste, but luckily there are 3 categories of radioactivity: high level, intermediate and low level waste. And this high level waste, which is mostly radioactive, is actually there in the smallest quantities. 99% of radioactive waste is intermediate and low level waste. Now, the current storage in the UK is generally on the surface or in shallow caverns. The main storage facility is a place called Sellafield, and this is one of the pictures from there with canisters in water. But this is not safe, long-term safe solution for high-level waste because it has the highest radioactivity. It is high heat-generated waste as well, and it has long life of radioactive decay. We are talking here now thousands and hundreds of thousands of years. So this is beyond anything that we do geotechnically that is 100 years, usually 120 years design life. And so the internationally adopted solution is to bury this high-level waste deep underground. So this is schematics of having disposal tunnels, maybe 0.5 kilometer to 1 kilometer in the ground. And these disposal tunnels contain this engineered barrier, which is a buffer here, compacted bentonite clay that protects the canister of already vitrified processed waste from essentially any radionuclides escaping into the natural environment, because that is a host formation. So the process here, bentonite is, as many of you would know, is a highly swelling clay. It needs to have a high density, it needs to be compacted to high density when it's placed around the canister. So therefore it has initially very high suction, and it has the processes going on in that bit of bentonite are quite complex, because on one side is the canister, which generates heat due to energy of the nuclear waste there. The current temperature barrier is 100 degrees C from the canister, whereas from the host formation, what is supposed to happen, host formation needs to have good bearing of water, so that bentonite can actually take the water in and hydrate and swell to seal in the construction joints and to reach the objective of having low permeability for any harmful materials to leach out. The behavior of the bentonite here is, again, complex when it's in the compacted state. If you look at pore size density versus pore size diameter, in the as-compacted state, it has dual porosity structure, so it has some larger particles and some tiny particles. So it has a macro and micro porosity. And what is supposed to happen during hydration is that all of this becomes homogenized with somewhere around here with microporosity. So this has requirements on a constitutive model. And where we are today, there isn't yet a GDF constructed in the world, because the solutions are still being examined. However, several countries have designed and built the underground laboratories where these full-scale experiments are being conducted, have been conducted using a heater rather than nuclear waste canister. So the objective for the buffer design is that hydration promotes the swelling and the sealing of construction joints and gaps, mobilization of design swelling pressure, because the rock, obviously, when excavated, would have relaxed the stresses on the boundaries, so the swelling bentonite must not crack the rock. And so existing international experience is based on laboratory scale experiments, then laboratory scale model tests like column tests, and full-scale prototype experiments in the field, and obviously numerical modeling. And our experience at Imperial has been built around development of numerical tools, obviously governing finite element equations, fully THM coupled and chemistry coupled, constitutive modeling of bentonite, looking at the temperature limit on bentonite, and groundwater chemistry. And we're working for 15 years now. We've been working very closely. This is the UK Agency for Nuclear Waste Disposal, international task force at European and international level, looking at these various aspects of barrier design, and then large European projects that have many participants, both from industry and from academia, but are led by these key national European agencies for nuclear waste disposal. And so what we use here is the same unsaturated framework as we have done before. The constitutive model is the same. What is enhanced in that constitutive model is the double porosity concept, micro and macro porosity. So the macro structure, the macro porosity, is the porosity within the aggregates of clay, whereas the micropores are inside the aggregates of clay. So between the aggregates and here is inside the aggregates. And there are some mathematical functions that are linking the two. Now, I showed this governing finite element equation with displacements, pore pressures, and temperature, but this can actually get more complicated. In the UK, because the sites, disposal site in the UK can be along the coast, so we have a saline water there, but also inside the mainland we have geology that produces saline groundwater. So chemical concentration can become one additional degree of freedom, and obviously now gas that is not at atmospheric pressure as in the previous formulation, but can be at elevated pressure. So we come here with this matrix being 5 by 5 at the moment that we are working with. So what we can do is validate this framework, starting as we expect, starting first from simple element tests, which are mainly, for this type of problem, they're mainly odometer tests with constant volume, swelling with a hydration boundary, so having here the measurements and having the model, so getting the tracing the evolution of the swelling pressure. Column tests that are meant to represent that duality of boundary conditions, so hydration from ambient temperature that would be on the rock side, and then heating at the other end that would be from the heater. So doing these tests and looking at how the temperature field develops with at the sensors that are measuring temperature and relative humidity, and also here looking the evolution of relative humidity with time, again, at these sensors. The role of vapor in the THM coupling is very important. So the formulations that don't have a vapor migration would not capture this initial, so in this lowest sensor that is closest to the heating boundary, the vapor will first increase the relative humidity, but then it will dry out as the time progresses, and will then pick up wetting once the hydration front progresses. So on the large scale, we have, this is the only experiment that we have, FABEX experiment, that was conducted in the Swiss underground laboratory, but the Spanish disposal concept, where they've had 2 heaters over a period of 18 years. So this is a cross-section that shows how the blocks of bentonite are placed around the heater. And this is the construction gaps that I talk about are essentially these gaps between the blocks themselves, and then the gaps between the blocks and the rock. And what they did was they ran the heating for the first 5 years, and then dismantled, so switched off the first heater, took some data to look at, and then the second heater was dismantled after 18 years. So those are some long-term measurements that we have, but clearly at the scale of the long-term that this problem has, this is not very much. So 18 years, this is color-coded sensors, this is temperature sensors. So next to the heater, gray lines, in the middle of the first ring, pink lines, and then second ring here, blue lines. At least we learn both from the numerics and from the experiments that the temperature field actually develops very, very, very fast and sort of remains stable within that period of 18 years. But relative humidity, you can see also then that some of the measurements are didn't exist at the beginning, then they picked up later on. Some here stop, some go on. So there is also, when we talk about the monitoring in the long term, there's always thinking about how these instruments are going to actually live and work over a long period of time. So again here, being able to capture next to the rock interface, relative humidity increases reasonably fast and almost saturates. Middle ring here again captured reasonably well. The ring next to the heater, has this initial vapor moisture, and then drying out, and then picks up again, but we really don't have very many measurements at that end. So that is one problem, the design of that engineered barrier itself. Clearly the host rock gets a huge environmental impact because the temperature here doesn't decay over the thickness of the buffer. So we are leaving here about 40 degrees C compared to 10 degrees C that was the natural temperature of rock at that depth. So there is a decay period, and the length within the host rock for the decay of temperature that have imposition of how we design the whole repository. So how many canisters we can place in each of the disposal galleries, what is the distance between them, and so on and so forth. So all of that is still not fully there sorted out, although one country in Europe, Finland, has actually already got the permission of their government to start to design the actual repository. In the UK, we don't yet have a decision on the site, so we can't even start to do anything. But we are underpinning the search for the site by doing this type of analysis. So for this application here, again, from our current experience, this is the most complex geotechnical example, has an extremely long design life and really multiple levels of coupling, including chemistry, and have strong demands on constitutive behavior. But geotechnical analysis can accommodate these complex phenomena. The European projects are actually, one of them that we participated in was designed to benchmark what people can do with a FABEX experiment and with other experiments, and how they compare, and then learn from all of that. The problem here, we are validating over short periods of time, but yeah, these analyses, these frameworks are currently used to produce a safe design. And so with the third part, this is the shortest part. What I just want to give you here is a flavor. This is not, we've started to work with tailings still about 5-6 years ago. And what we do here is mainly exploratory studies to learn to understand how these structures should be modeled, can be modeled. And then what are the important things about them? What needs to be assessed? And we are working here with industry, but doing PhD or master projects, final year projects, where we can actually explore these things. So one example here is, first of all, this was the first PhD of David Solans, who was actually working in tailings industry in Chile before coming to do a PhD with us. So he had data on a particular, actually several tailings facilities, but this tailings facility had some measurements with accelerometers at the crest and at the toe, at the base of the dam. So the objective here was reproducing reliable state of the tailings facility, because this is a very time-related construction, thinking about appropriate mechanical and hydraulic boundary conditions, maintaining the freeboard. Does that matter? Does that not matter? And things like that. So this sketch here shows the elevation in meters above the ground level, and time in years. This was about 20-25 year construction. So there's some 8 rises here. Starter dam was the first, and then keeping 2 meter freeboard between every successive upstream dam, this is downstream dam, and the construction of slimes. So what is shown here is this particular case study had a 200-meter beach and then pond in the distance, and we started constructing layer by layer, keeping the beach, and obviously the pond remains whatever it is to the boundary of the finite element mesh, and doing that for every elevation. And then during the construction also here, we are able, in our approach that we do every layer, we prescribe the void ratio for the slimes and for the sand as well. That was estimated from the site. And what we had here that was very useful was a set of CPT tests at the crest of the dam, 3 of them that were interpreted here with Robertsons, with Bean and Jeffries, and some other interpretation. So showing that so the upper part of the dam is more dilative, obviously, than below. But our model, if you can see here, so our model here has reproduced reasonably closely, so has captured that increase near the top, but also at the bottom, the state parameter within this crest here. The minus 0.5 is what is uniformly adopted as a value of the state parameter that marks the possible onset of liquefaction. So that took quite a lot. That was the first one that we did, and David Solans took a lot of effort to actually do it step by step with proper application of boundary conditions. But then applying the earthquake record, the Illapel 2015 earthquake record, he was able to show, again the colors here may not be quite clear, so the red color is the model and the blue color is the recorded. On this side is the acceleration response spectra of the crest of the dam, and on this side is the response amplification spectra, so the ratio of crest over the base to show what the amplification is. And the model has, seems to capture that reasonably well. And the dam has not failed, so I don't have time here to show the other results, but the predictions that David has for movements, they're all very small and very, very shallow. So the dam, after the earthquake, visually didn't get deformed, and our model was reproducing the same. Then this example here was assessment of a filter tailings. This was a master project of a student who also worked for one of the tailings companies in Peru, and she brought with her this case study of a filter tailings. But we didn't have any measurements there. There was none of the testing that was performed with this material was unsaturated testing at all. So what Joanna did was to essentially do, again, look at the literature for what would be materials close to this particular tailings material in terms of water retention curves, and look at the effect of the water retention behavior. The other aspect that they were interested in was a drainage layer here, and what is the effect of that drainage layer working or not working. So in the model, in this set of pore pressure contours that we have here, this is a phreatic surface. So the axis of symmetry here, that is a 12 meter from the foundation level. The dam, this stack also has a starter dam to give the shape that they finally was constructed. So with a drainage level permeability of 10 to minus 3 meters per second, this phreatic surface rises here to 12 meters. But then, again, parametrically, we reduce the permeability to 10 to minus 4, and the phreatic surface rose to 33 meters, so actually quite high. So there's many things that we did here as an exploratory study, just to give some of them are in a small conference paper that we published subsequently. And then the other thing that we were asked to look at was this retrofitting of tailings facilities. This is again an MSc project. Nicolas de la Maza came also from Chile to do a master with us. And this was the case of centerline tailings being constructed first, then extended with upstream tailings, and then after some time being used to continue with the filter tailings. So the slurry deposition was stopped, and they thought of continuing with the filter tailings. So this was not done. This was not done. So that is, we were asked to look at what would be effect of having that on top. And again, there is many details there, but just to sort of look at just a static operation of the dam, with the end of the upstream slurry tailings, the factor of safety of this facility, so numerical factor of safety, was 1.3, but adding this another 30 meters of filter tailings reduced that to 1.04. And then when we applied on that whole facility, then we applied the ground motion that was the same ground motion that David Solons used. Obviously, there is a failure here. So these are contours of horizontal displacement that essentially are extremely large, but yeah, the failure here, this detail shows the vibratoric plastic strain contours that indicate the formation of the slip surface already within 3 seconds of the earthquake with this thing on top. So, as I said, this is what we do currently as so exploratory studies to understand how to model them. So Nicholas here was also modeling the whole construction sequence over a period of time and everything else. So we are not just taking that as a final geometry and doing something with it. Construction sequence is very important. So that is where our capability and capacity is. So these two are complex geotechnical examples. What is lacking often is that detailed construction sequence, because some of the structures are obviously quite old. It is difficult to sample in situ, you know that better than us. So getting to understand what is the state in situ is not easy. And what we have found is most laboratory testing on these materials is still predominantly saturated. So not very little unsaturated testing is done, like places here in Pretoria. So geotechnical numerical analysis can accommodate these constructions realistically, at least the way we do it. But there is a lack of monitoring data to validate, again, for numerics, especially when we are looking into the long term. For life cycle assessment, having the monitoring data in the long term is really, really important. And so, just to conclude with a few overall points from this. So life cycle assessment of geotechnical infrastructure is complex because it requires a coupled approach. So it's not drained or undrained, it really is coupled. And soil being multi-phase material and having the structures like this are exposed to atmosphere, we have to take that into account. Why numerical? Well, there isn't really much else that we can use to assess this, the life cycle for any of these structures and to quantify the risk, but to do numerically. Again, infrastructure monitoring, we keep sort of repeating that time and time again, is really crucial to provide the field data. I mean, rainfall is monitored in many countries, is done as something that is regular. The rain gauges in weather stations, but as a profession, it would be really nice if we take the responsibility for long-term monitoring, in particular as much of our industry these days is moving towards the machine learning generated approaches that actually do depend on input from field measurements to keep the projections going. Most importantly, apart from field monitoring, the experimental characterization of geomaterials, especially unsaturated in the laboratory, is really a must for this type of infrastructure. And with this, I thank you for your attention very much.
Okay, great. Thank you, Professor Zdravkovic. That was a really insightful lecture. I'd like to open the floor to some questions before I give the gift. Do you have any questions? Would anyone like to ask any questions? Yes, Paul. Oh, Yolande's got a mic. If you could just say your name and then ask a question, please.
Hello, hello. Hello? Hi, thank you so much for your lecture. I really enjoyed it, especially based on my history in tailings and also some research that I did on unsaturated. My question is regarding the earth infrastructure example you showed, regarding the life cycle analysis of that railway embankment on the London clay. It's coming very much from a point of in-practice engineer. I want to know, like, how long does it take to do such a life cycle assessment? And you know, using these numerical methods, how long does it take to do such an analysis, excluding the gathering of data? And then the second part of the question is, like, what is your experience regarding, like, the evolution of technology and computing to be able to start applying these sort of numerical methods in practice rather than just in research?
Thank you. That is a very good question. So, if we are looking just at the runtime of these analyses, what we use, let's say, for our analysis is a server, Windows server. In the past we were always working on Linux, but now with so easier transfer, student access, and remote access, and everything else, we are working with Windows servers. I think analysis like this that we performed on this embankment is had taken at the time, and this is on an older server, about 3 days, because of the length of the time that we were looking at, and all the nonlinearities that have gone in. So by comparison, that is now actually reasonably fast, because we do this first analysis is there, it has to be done, so that we can understand what we can simplify in going forward, and whether we can derive then something that is accurate but can be done much faster. I mean, we haven't done that yet for this type of problem, but we have done that for offshore industry, for wind turbine foundations, because they had a problem of advancing the design methods for these very large monopiles, and they realized that existing design methods were too over-conservative. So what we did for them was perform the whole suite of full 3D analysis, very careful for different materials, and we then for looking at the mechanisms of how these monopiles behave, we realized that it's not only PY behavior, which normally for laterally loaded piles exist in the design codes, but there would be 3 more soil reactions, like distributed moment from the shear stresses, and also on the base. So we then, from about whatever it was, about 100 3D complex analysis, we develop the design methods on a Winkler approach, with, in addition to just horizontal spring, additional 3 springs to give the full response of a 3D monopile. So that is the approach going forward. The other approach going forward that I mentioned is the data science, so the machine learning with neural networks, Bayesian inference, where again we can do a batch of 3D analysis to train these simpler models, and then on a more regular basis apply the simpler surrogate models. But we can't really go away straight away without understanding the problem fully. So that is where the full analysis needs to come first, if that answers your question.
Okay, great, thank you. Are there any other questions? Lidija, Prof. Jacobs.
Thanks, Yashay. Lidija, I just want to ask, the factor of safety that you calculate from your analysis, is it the strength reduction type analysis or something different?
So it is not, well, okay, strength reduction. Strength reduction, it is strength reduction, but the factor of the factor of safety that we have is not applied to just a more Coulomb or critical state line and trying to get it down. It is taken in as one of the hardening parameters within the constitutive model. So for any constitutive model, we add that as a hardening parameter, and then there will be a change that applies to the model itself, to the right-hand side, so to the model, to the hardening part of the model, but also to the finite element formulation with the right-hand side correction of the finite element equation, of the governing equation. And therefore, when we perform this analysis in our code, what we say now is normally factor of safety is not in the analysis before we activate the factor of safety. So it starts from 1. So we would then say, okay, start to increase factor of safety by, let's say, 0.1 and so on, and that would then start to reduce by the stress change that exists there, start to reduce the strength. So at the end, when we have a clear failure, we have the factor of safety value, which actually has given us also how much the strength has reduced. But it is not just. I think in some software, whatever model is used, when it comes to strength reduction, they will just say, okay, that is now the more Coulomb surface, and actually through the solution of the governing equations, they start to reduce that yield surface and correct where the stress point should be so that it doesn't violate the yield. But the way we have done it is consistent for any model and whatever the yield surfaces are. And it is implemented in all our models.
Thanks, Lidija.
Thank you, Prof. Are there any other questions? Mario.
Hi, thanks. Okay, hopefully a quick one. Just based on a brief comment you made when you were going through your embankment. You mentioned you've got rainfall on the embankment, and then you said it either infiltrates or it doesn't. What is that governing factor? Is it the hydraulic conductivity? And if so, is it just two numbers that you're matching up to see if one is greater than the other, or?
So yes. So the precipitation boundary condition will compare the infiltration that at an increment infiltration that needs to come in, and then what is the permeability in the soil that exists at that time, and it will look at both what happens at. So if you first look at what happens in terms of the tension in the soil, so whether there is any cracking, and then we'll check what happens due to suction. And so if both of those are saying that the permeability is less than the infiltration rate, then that water will essentially pond or run off. But if they can go in, it will come in and change the suction in the soil.
Okay, thank you, Mario. Any further questions? Nothing else. Prof, if I could ask one.
Yeah, sure.
Unsaturated soil mechanics can be quite daunting to some, say, practicing engineers. If you were to suggest some laboratory or element or classification tests to understand some of the unsaturated soil characteristics of your soil, what would you suggest?
I think the most telling, probably most visual, is the retention behavior, because that relationship and simply between the degree of saturation and changing suction is describing actually the soil itself. So something like London clay will have a very high air entry suction, so will be saturated for reasonably large value of suction, whereas something like silty sand will have a very small air, so it will start to essentially change very quickly in unsaturated conditions. That would be that's really the most visual test that. And to be honest, if you look into the numerical analysis, that is really the key sort of thing that we would want to have dealing with unsaturated boundary value problem.
Okay. Thank you, Prof. I just want to get a gift. We've got a small gift for you. Thank you, guys.
Thank you, Yashay. Thank you very much. Thank you. Thank you very much. Thank you. Pleasure. Thanks.
Thank you again, everyone, for coming. I hope you enjoyed the lecture. I found it fascinating. Prof. Zdravkovic is here afterwards, as well as Professor Potts and Dr. Gaspar. They'll be here to please join us for some snacks, and we'll see you afterwards. Have a good evening, everyone.